Hello, I am Sai Ajithesh Renjinthala. Today, I am presenting a critical review of smart contracts as database automation. My research explores how blockchain has moved beyond a static ledger to become a programmable and active database engine. We will examine the architectural transition from centralized systems to decentralized protocols and identify the technical gaps currently hindering the enterprise adoption. Specifically, we will look at how trust is being redefined as a computational construct rather than an institutional one. By the end of this session, you will understand the paradox of using immutable code in a volatile market and why code is law is a challenging concept for traditional database administrators. Traditional DBMS systems rely on centralized authority, which creates a single point of failure. Blockchain signifies a shift towards distributed ledger technology, or DLT. As Nakamoto observed in 2008, this allows transactions to be recorded without reliance on trusted third parties. Data integrity is ensured through cryptographic hashing, making tampering computationally impractical. This move towards decentralization is not just a change in storage, but a paradigm shift in how we manage data ownership. In this new model, the information is not protected by a firewall, but by a mathematical impossibility of altering history. This effectively turns the database into a transparent, chronological sequence of events that everyone can verify independently. A primary concern for decentralized databases is storage and bandwidth. We solve this issue using Merkle trees. By hashing transaction blocks recursively into a single root hash, we can maintain global integrity while allowing for lightweight clients. This cryptographic abstraction allows nodes to verify individual transactions without storing the entire blockchain history, making the system significantly more scalable. The beauty of the Merkle tree is its recursive nature, where individual hashes are paired until the root remains in the block header. This means that we can prune intermediate hashes that are no longer necessary once a transaction is sufficiently buried in the chain. It provides a mechanism for growth that doesn't exponentially increase the hardware requirements for every participant in the network. Smart contracts are computerized transaction protocols that function as decentralized stored procedures. Within the blockchain's 6-layer taxonomy, these live in the contract layer. Unlike traditional triggers, smart contracts are deployed across every node in the network, ensuring that the agreement is written directly into the code and executed autonomously. The execution of these contracts depends heavily on the underlying network type, whether it be public, private, or a hybrid consortium model. Each of these represents a different optimization point between absolute trust minimalization and high performance throughput. By integrating these protocols, we are essentially moving from passive data storage to an active programmable environment where logic is globally consistent. One of the most significant hurdles is the Oracle problem. Blockchains are isolated environments. They cannot natively fetch data from external APIs or even legacy databases. While oracles act as a bridge, they introduce a massive risk. The decentralization of the blockchain is compromised if the contract relies on a single potentially corruptible data source. This creates a deterministic gap where the smart contract is only as reliable as the data it receives from the outside world. If an oracle provides false information, the smart contract will execute that false logic immutably and irreversibly. Solving this would require decentralized oracle networks, but even then, we face the challenge of bridging two fundamentally different trust architectures. While immutability is a strength for data integrity, it is a liability for software logic. Unlike SQL procedures that can be patched, smart contract code is immutable once deployed. Logical flaws such as reentrancy attacks in the DAO hack can lead to irreversible losses. This is why my research emphasizes the need for formal methods and pre-deployment security protocols. We must recognize that immutable code in a volatile market is a high-risk endeavor that requires a new way of thinking about software development. Developers can no longer rely on hot fixes or patches. The code must be mathematically verified before it even touches the mainnet. This highlights the urgent need for verifiable formal methods that can prove the correctness of a contract's logic before it manages real-world assets. We must also address the scalability trilemma, the struggle to achieve decentralization and security without sacrificing speed. Current market solutions suffer from high latency compared to traditional DBMS. While a centralized SQL database can process thousands of transactions per second, decentralized consensus protocols currently operate at a very tiny fraction of that rate. This performance gap is largely due to the computationally expensive puzzles required by proof-of-work systems or the communication overhead in the proof-of-stake. While we are exploring sharding and layer 2 solutions to split the ledger into parallel pieces, they are still in the early stages of enterprise adoption. Until we can match the throughput of traditional relational databases, blockchain will remain a niche tool for specific high-trust use cases. In conclusion, while smart contracts offer unparalleled transparency and integrity, their future depends on bridging the Oracle gap and solving scalability constraints. Innovations like zero-knowledge proofs and sharding are promising steps toward a future where decentralized automation meets the performance and privacy requirements of modern digital economy. We are looking forward towards a future where participants can ensure correctness without revealing sensitive data, moving past current standard of raw, pseudonymous transaction feeds. As behavioral analysis becomes more sophisticated, privacy-preserving technologies will become the next major theme in the evolution of DLT. Ultimately, the goal is a system where decentralized automation provides the speed of modern economy with the security of cryptographic proof. Thank you for your attention.